talk for the afternoon. And it's going to be given by Professor Heath-Brown. And the title of the talk is, God, I just met, it's like 4 words. And it has powers as values of polynomials.
And you can count up to 4?
Roughly.
Something like that.
Well, thank you very much. It's a pleasure to be here talking to you. It's been a pleasure to be here at this arithmetic statistics session. I've learnt lots, and I'm going to try and put some of it into practice, because one of the things I think I've learned is that when you have 3 boards, you need to start with the middle one. So we'll see how that works. I'll start with all 3 middle ones, yes. So this talk is designed as an advertisement for some joint work with Lillian Pearce. So let me explain straight away what the basic problem I'm interested in is. So we're going to have a polynomial f with integer coefficients. It's a polynomial in n variables. And I'll call the degree capital D. And we're going to be interested in the equation in which f is a perfect power. So we're going to be considering the set of vectors x in Zn, which f of x is y to the d for some perfect power y to the d with a specific value of little d, and we're going to consider solutions in a box of size b. And we'll call this quantity n of b. So the question in which we're interested in is how often is the value of this polynomial a perfect d-th power? Now there's a very crude heuristic that you can use to suggest what the answer might be. So if a number n is of size at most, well, let's call it y to the d, that might be suggestive, then n is a d-th power in exactly y cases, 1 to the d up to y to the d. That's a proportion one in y to the d minus 1. And so the probability that n is a d-th power is roughly 1 over y to the d minus 1. Or for numbers, well, let's see what size we're really interested in. Little f is a polynomial of degree capital D. The variables take size up to capital B. So f is of size b to the d, and so we expect it to be a d-th power with probability 1 over b to the d to power d minus 1. And so you might expect that the number of times you get a perfect d-th power, well, there are how many x's? B to the n. So you might expect that number of perfect d-th powers. And there are I'm sure you can think of many different reasons why this might not work. However, well, if you can't, let me point out that I haven't said that little n, and compared the size of these, what would happen if little n was smaller than d times d minus 1? This would suggest that n of b is positive but tends to 0 as capital B grows. That's pretty implausible. However, one can apply the circle method to this type of situation, and if the leading form of f is smooth, that's to say, if out of f you take only the terms of degree precisely capital D, that will produce a form of degree capital D, and if that form is non-singular, then you will get, well, let's say you should get constant b to the n minus d minus 1 times d solutions, roughly, under a condition that the number of variables is sufficiently large, n greater than or equal to d minus 1 times 2 to the d. The leading power, the leading form in that case would be a perfect D's power, which would not be smooth. So if you have enough variables compared with capital D, everything is fine under this smoothness condition. Now this question is related to a conjecture of Serre. Little d does not enter into this inequality. No.
Gigantic.
Yes.
Fraction in the second line on the second board.
Have I got my little d's and capital D's mixed up? Perhaps that's my problem. Yes, I think I have been sufficient. I have been too imprecise here about the degree of imprecision in my statements. I should have been less precise in my claims. So I was saying that you expect normally to be able to prove something like this, and there are lots of expects and normalies in there. But the point that I'm making is that you can handle this situation if little n is large, well, let's say in terms of capital D and little d. Large enough n, they're good. Now this is connected, as I said, with a problem of Serre. So Serre looks at a finite cover of Pn minus 1. So, for example, you might imagine that x was given by the vanishing of a form in x1 to xn and y. So this would be give you something in Pn, and you would map this to x1 to xn. And so the notation is set up to correspond to what I have there, except that in my case I don't necessarily have a form. And then Serre asks about the counting function, which is the number of points p in xq for which the height of the image is at most b. So what's that saying? You would want x1 to xn to be of height at most b, and you want a point P, that's this point here, to have rational coordinates. So you'd want not only x1 to xn to have rational coordinates, but y as well. So he's asking, for how many rational x's is there a solution of this in which y is also rational? Now, it's a cover of Pn-1 in the sense that, geometrically, for any values of x1 to xn, you will find a y in Q bar, which solves this. So the question is not so much for which values x1 to xn does this have a solution, but for which values x1 to xn is there a rational solution. And then you won't expect to get all values of y. And indeed, that's exactly what the counting problem is reflecting. So for not all rational x1 to xn will there be a rational solution y, and that's similar to the problem that I have there, and if I was looking at the homogeneous situation, it would correspond pretty precisely. Now, Sayre conjectures that this number grows at worst as far at the rate b to the n minus 1 times the power of log b. For covers of degree at least 2. So that's to say that you, well, not only do you not get all of Pn minus 1, but you only get a small number of points, only b to the n minus 1, basically. And in this degree of generality, that's the best exponent that you can hope for.
Sorry, could you give a definition of finite cover?
No, I'm not going to. What I'm going to say is that this situation in which if I take f to be homogeneous with a degree which is a multiple of d, this will give me an example. This situation will give me an example of this. So that's perhaps what you should think about. That, I'm not saying that these are the same problem or that one is a subset of the other, but they have a common subset. So the problem that I'm interested in is related to this question of Sayre. Sayre himself proved that you have an estimate with exponent n minus half, and this used the large sieve. So Sayre's not famous for being a sieve theorist, but he did use the sieve for this. Where? This is in his lectures on the Mordell-Weil theorem. So there is some general results that I should mention. So Broberg has considered the case n equals 2 and given, for Sayre's problem, a bound b to the 2 over d plus epsilon. And you can see that if d is 3 or more, that's better than Sayre was asking for. And if d is 2, well, it's almost what he was asking for. I suspect that Broberg, if he worked harder, could have replaced that by a power of a logarithm. Broberg also had results for n equals 3. And there he gets b to the 2 plus epsilon, providing the degree is at least 3. And again, that's virtually what Sayre was asking for, apart from the epsilon, and probably that could be removed. But in the case when n is equal to 3 and d is equal to 2, one doesn't quite get Sayre's conjecture. he was only able to get exponent 9/4. So even for these low-dimensional cases, we're not quite at Sayre's conjecture. So now I'm going to talk about the special case of polynomials representing powers, and these correspond to cyclic covers. And indeed, I'm going to impose a smoothness condition, which lets us go a little bit further. So I'm going to assume that in this situation here, we'll take the leading form of f to be smooth. So to avoid confusion, let me put cyclic covers in brackets. So I'm going to consider the general case where you have a polynomial, not necessarily a form. So that's a generalization of the problem where you have a form, but these correspond to cyclic covers. So in this case, the result of Wunsch, which refers to arbitrary dimension. So I'll phrase this in terms of my function nb, which is the counting function for polynomials equals dth powers, but that translates into something about covers. So Wunsch got exponent n minus n/n plus 1. So you see that, again, this doesn't quite deliver n minus 1. Gets close for large n, which sort of, I suppose, the circle method approach also did well for large n, so you might think you're in the same ballpark. And so finally, the result that justifies my being up here, under these same conditions that you're talking about powers represented by polynomials, and you insist that the leading form of f is smooth, we show that the counting function is of order at most, well, slightly unpleasant exponent, but you can see, I hope, that for large n, this is roughly n minus 3/2, better than Sayre was asking for, and indeed it gives you b to the n minus 1 log squared b for n at least 9. Is that right? That's what I've got written down. So comparing with, for example, the circle method had lower bounds for n that depend on the degrees. This lower bound does not depend on the degree, except in as much as we need the degree to be at least 3. However, we do require this smoothness condition. Well, just as the circle method would have done. But Sayre's conjecture relates not only to covers whether they're cyclic or not, but also does not insist on a smoothness condition. The implied constant I should mention here, well, let's say that it depends on f and d. Yeah, and therefore on capital D as well. So these results here apply to the situation as there where little f is not necessarily a form, but that's just, well, the key case is when little f is a form, in fact. Okay, so you can get to Sayre's conjecture, at least if the dimension is large enough. So just how large, this is an issue of ongoing research, but this is the point at which we are now. So I want to explain now the underlying idea behind these sorts of theorems, because I think it's quite elegant. And it uses a method in which one sieves to detect perfect powers. So we want to detect perfect d-th powers, so we're going to choose primes p that are 1 mod d. And for each such prime, we'll choose a character chi p of order d. So this is chi p, a character modulo p, that is. I'll introduce the function wk, which counts how often the polynomial takes the value k. So this will be the number of integers x with size at most b, for which f of x is equal to k. And then the key fact that we're going to use with these characters to pick out perfect powers, we'll choose q, which will depend on b amongst other things, and we'll look at the sum of these characters where the prime ranges over the interval from q to 2q. And we'll sum and square this. I guess I'll put modulus signs on. So this is greater or equal to 0 for all k. But if k happens to be a perfect d-th power, these terms will all be 1. Well, unless p divides k. So it's at least so this is a key, simple key observation, and I'm going to ignore this condition because that's just a fly in the ointment. Sorry? Yes, that's going to be an assumption throughout this. But little d is fixed, of course. Let me write q0. Well, let me say that now. It's the number of primes congruent to 1 mod d, for which the prime is, so these are the primes over which I'm summing, and q0 will be the number of them. So using this fact, you can see that q0 squared times if I only count the ones which are d-th powers, that will be less than or equal to the sum over all k times this square. So here I will get something which is non-negative in general and something which is at least q0 squared when I have a perfect power. And now, if you expand this, well, first of all, there are the diagonal terms. And then there are the non-diagonal terms. that. And the number of diagonal terms is, of course, Q0. And one obtains the following lemma, which one can use to count dth powers. Well, here I've set wk to be the number of representations by the polynomial, but one can use this for an arbitrary sequence. So I'll phrase this with an arbitrary function wk, which I'm going to assume is supported in a set of positive integers up to e to the q, and then some wk, these are non-negative functions, k is a dth power, is less than q naught inverse some wk plus q naught to the minus 2 some Okay, so this lemma is correct as stated, I hope. So I've been waffling a bit here and there. I've ignored various things, but this condition that k is at most e to the q is enough to take care of this condition, for example. So how should we understand this lemma? We're trying to show that relatively few of the numbers k are dth powers. This main term is good. No, only a proportion 1 over q naught is allowable here. So what one would need, well, there are the number of pairs of primes is of order q naught squared. So all you would need is some degree of cancellation in this sum to prove that most numbers are not perfect dth powers. So if you estimated this sum trivially, you would find that some wk, where k is a dth power, is less than or equal to some wk in general. But there's no loss in the lemma, and any non-trivial bound here will give you a gain. So the issue reduces to giving non-trivial bounds for some, well, in our case we're interested in wk will be counting values of polynomials So you want to give a non-trivial bound for something like that. For each prime, you choose any dth order, character of order d, and then fix that prime. So it's certainly non-canonical, but given that d is once for all fixed, there's no loss in doing that. Sorry? D equals 2 works just fine, yes.
So is this factorization?
Yes, yeah. So what do we know about sums of this type? Well, what we have here is a character to modulus P1 times P2, and it would be much more natural if we had a summation over the entire range modulo P1, P2. So if you were to look at x running mod q, for example, and had some character chi mod q of f of x, this would be a nice natural object to study, and it would have multiplicative properties with respect to q, for example. And in particular, if q is prime, one can use estimates of the Deligne type for this. And in the situation that we have here, there's a results of Katz that show that this is of order q to the n over 2, using the fact that the leading form of f is smooth. Now, that's fine if you have a complete set of residues here. In our situation, we don't, but there's a standard procedure for passing from the incomplete range to the full range. And the result is that if I call this sum here S, you can show that S is of order, well, the modulus in our case is P1 times P2, with a loss that is of order log P1, P2. But the key point I'm making is that the power of this comes from a Deligne type estimate, and that in doing that we're taking the range here and converting it into the full range. And you might imagine that there is, if capital B is smaller than Q, you might imagine that there's some loss in doing that, and indeed there is. In this case, maybe there is, but all right, let's keep Henrik happy. Well, let's see what that does in the lemma. So we would have Q naught inverse, that's here. So this is counting for all k the number of ways of representing k as polynomial. So that will give us b to the n, since that's the number of values for x. Then we've got our term q naught to the minus 2. The number of pairs of primes is going to be q naught squared. And then these sums we will have, well, the first prime is of size of order q, so it's the second prime. We've got the exponent n over 2, and then we've got something that looks like a power of log q. And so this will be q to the minus 1 times b to the n plus q to the n over 2 times various logarithms. And now you have you can see it's the time to decide what size capital Q should be. And we haven't said what size capital Q should be, but we're going to choose it to balance these two terms. Sorry, that's q to the n there. So we're going to make q to the minus 1 bn equal q to the n. So we choose q to be b to the n over n plus 1. And the result is that we get b to the n minus n over n plus 1 times logarithms. And this is the result that Munshi got. So you take this sieving device to pick out these powers. You have a character sum to deal with. It's got a range with variables up to size b. You convert that into a range of size up to the full modulus, and you use a Deligne-Katz type estimate. Now you can see that capital Q is around b in size. And that means that the modulus, which is P1, P2, is around b squared in size. So in the sum S, the range you're taking here is around the square root of this modulus. So the Deligne estimate, q to the n over 2, well, if I did the trivial estimate, that would be b to the n over 2, b to the n. The trivial estimate and the Deligne estimate are pretty much the same power. So we're getting to the point where there's not a lot of saving to be got by this route. And indeed, if we were to try to take capital Q any larger, well, the method would grind to a halt. So the problem in making further progress is to better this procedure of completing this exponential sum and using the Deligne estimate directly. So we have sums where the length of the variables is around the square root of the modulus. And it's exactly at this point that the Deligne estimate loses its efficacy. So what we're going to do, and this is the new part of the work with Lillian Pierce, is to use what we've called the Q analog of van der Corput's method. So van der Corput's method is a method that's well known in connection with estimating exponential sums in the sense of the Riemann zeta function, etc. But it can also be used for character sums in a restricted setting. And the restricted setting where it works efficiently is when the modulus here is composite, highly composite. And when I described the sieve method, I said that we would be using primes, and you can't factorize primes. So the idea is that you should replace these primes by things that are composite. And there's no reason why you can't do that in the formulation of the sieve part. So we'll replace the prime P by, well, it turns out that it's enough to have things that are composed of two prime factors, U and V. And in fact, it's appropriate to choose one of them smaller than the other you choose u to be around the square root of v in size. So that's a technical point that is what's best for the proof. But having done this, you still encounter exactly the same problem, but now this modulus here is, well, previously it was P1 times P2, so that's going to be the shape U1, U2, V1, V2. And because we've chosen P to be composite, we've got various factors that we can play around with here, and we're going to write this as a product Q1, Q2, with Q1 being U1, U2, and Q2 being V1, V2. So this modulus that we have here now factorizes in a convenient way. And how can we use that to gain some mileage in estimating the character sum? Well, we're going to introduce a parameter h, which is the integer part of b divided by q2. And we're going to write down h to the n copies of the sum s. So for simplicity, I'll assume that the summation condition is that the xi's are positive integers at most b. That's not quite how I formulated it before, but that's going to be rather easier to explain here. And then we'll rewrite this by shifting these variables by q2 times h. And so, well, let's call this a new variable t. So the range for t is now minus q2 hi less than ti. It's quite a complicated thing, but it's still an interval. And then we'll change the order of summation. And we'll have to keep track of the size constraints. Well, t here, the largest that it can be is capital B, and the smallest that it could possibly be is minus b. But then the conditions on the hi, well, for each value of t, this gives us a condition on the hi. Well, let's just say that hi is in a certain interval that will depend on x, as well as hi being at most capital H, but t. So you get unpleasant conditions here, but they still only mean an interval. And then you apply Cauchy's inequality. Like that. And you expand. So you get, well, you then have two different variables, h1 and h2, and you have the variable t, and here we have chi q f of t plus h1 q2, sorry, and there are more unpleasant summation conditions, but nonetheless, the point here is that for given h1, h2, the condition for t defines some sort of interval. It's an interval at least. And finally, we make one more shift. We'll call the variable s, and write this as chi q of f t, s plus q2 times h1 minus h2, and then just f of s here. And finally, you can see what the payoff for all this hard work is. When you look at what we have here. So this is effectively chi q of, let's write it as f of s plus q2h over f of s. And then I'll rearrange things like this. And what you have in the numerator here is a multiple of q2. So it's q2 times some rational function of s. Now this modulus q was q1 times q2. But what we've produced now is a function of s that has period only q1. So we've reduced the effective modulus. Let's just say that as this. So the effective modulus has been reduced from q down to q1. So when we're estimating these character sums, originally we saw that the Deligne estimate becomes ineffective when the length of the sum is root q, or smaller. But since we've reduced the period, we can now expect non-trivial bounds for this sum, because it only has modulus q1. So we're good if b is bigger than root q1 now, whereas previously the condition was that b is bigger than root q. Now you can imagine that all this manoeuvring, though it's been good in some ways, there's been some losses, and therefore the amount that you save isn't as big as you'd like. But even so, this crucial fact that you've reduced the modulus by this procedure, by introducing this factor q2 here, is the critical thing that gives you this extra saving. And allows you, when you have a composite modulus, to do better than you would get directly from the Deligne procedure. So I hope that's given you an idea of what's involved in this theorem. Thank you very much.